Before we start talking about characteristics of atoms and how we can actually use the periodic table in order to anticipate trends in these characteristics, we first need to talk about Coulomb's law because it plays a vital role in these trends. Coulomb's law addresses electromagnetic forces, and specifically electromagnetic forces are the attractive forces that act between electrically charged objects. So in this case, electrons and protons. Now he noted that the electromagnetic force, the magnitude of the force, is directly related to Q1 and Q2. Now Q1 and Q2 are the magnitude of the charges of the objects, and it is inversely related to the distance between these objects. More simply put, the force when the charge of the two objects increases, then the force also increases. When the distance, d, increases between the two charged objects, the force actually decreases, and k is just a constant. Now keep in mind we're talking about Q1 and Q2, so if the force is negative, meaning Q1 is positive and Q2 is negative, or Q1 is negative and Q2 is positive, resulting in a negative force, then there will be an attraction between the objects, which makes sense because protons are positively charged, electrons are negatively charged, and they're attracted to each other. Similarly, if Q1 and Q2 have the same charge, and therefore the force is positive, then there will be a repulsion between the charged objects. What this should make you think, though, is, well, if protons repel each other, why does the nucleus stay together? Why don't protons just repel each other and prevent the nucleus from sticking together? And the answer to that is the strong nuclear force. Now, the strong nuclear force is stronger than the electric force, and therefore it can hold the nucleus together. So it counteracts the electromagnetic repulsion between protons and enables the nucleus to stay together. We're now going to talk about an important concept, effective nuclear charge. So just as review, according to Coulomb, the attraction between an electron and a nucleus depends on the nuclear charge, which was your Q1 and your Q2, acting on the electron, and the distance between the nucleus and the electron, that was your d. It's not that simple, though, because while in an atom electrons are attracted to the nucleus, they also repel one another. So if you have multiple electrons, they're not only being attracted to the nucleus, but they're repelling one another. And so as a result, we have to define this effective nuclear charge to better understand what is happening in an atom. The effective nuclear charge is the nuclear charge acting on an electron, taking into account the repulsive effect of other electrons. So we're not just looking at the nuclear charge, we are looking at also the impact that electrons have on that attractive force. So this right here is how we actually calculate the effective nuclear charge. It is Z effective equals Z minus S. So let's define these variables. Z is the number of protons, and S is your screening constant. What that is the portion of the nuclear charge that is screened, I often say shielded, from the valence electron by other electrons in the atom. Now, the screening constant is normally just the number of core electrons, the number of electrons closer to the center of the atom that prevents the valence electrons from being attracted to the nucleus. It is important for you to remember, looking at the effective nuclear charge, the effective nuclear charge is always going to be less than the actual nuclear charge. And the reason why is when we're thinking about just the nuclear charge of any atom, let's say it has 11 protons, we're not considering the shielding or screening effect that core electrons have on valence electrons. Core electrons decrease the attraction valence electrons have for the nucleus. And so as a result, we had to come up with this effective nuclear charge in order to get a better estimate of how attracted electrons are for the nucleus, because if we assume that electrons have no effect, that's not an accurate gauge of the attraction of valence electrons for the nucleus. So let's look at the trend for the effective nuclear charge and what happens as you move across the periodic table and down the periodic table. Let's start with talking about down a specific group. What happens? Well, the effective nuclear charge doesn't change significantly as you move down a group. However, it does slightly increase, and the reason why it increases is because electron cores increase in size, and as a result, they are less able to screen the electron. So as a result, the effective nuclear charge increases. When we're talking about what happens when you move across the periodic table, again, the effective nuclear charge increases, and the reason why it increases is because the number of protons increases, but the number of core electrons stays the same. So if you think back to the formula, Z effective equals Z minus S, Z is increasing, but S, which is the core electrons, is staying the same. The first characteristic that I'm going to talk about is the size of atoms and ions. Now, there are two different definitions I have to specify quickly, and that is the difference between bonding atomic radii and non-bonding atomic radii. Bonding atomic radii is the distance between nuclei of atoms when they are chemically bound together. And so if you look at this diagram right now, these two atoms are bound chemically together, and to find their radii, all you have to do is measure the distance between their nuclei and divide by 2. Non-bonding atomic radii is the distance between nuclei of two atoms that have not been bound, but they have collided. So they're just touching, not like in this diagram, but they're just touching, and then you find the distance between their two nuclei and divide by 2. As you can see, or as you can imagine, the distance for a bonding atomic radii, the size of it, would be smaller than that of non-bonding atomic radii. As you can see, when they are bound together, their nuclei are closer together than in non-bonding atomic radii. So let's talk about atomic radii and the trends that you can see in the periodic table. Now, we're first going to talk about as you move down a group. As you move down a group, the size of the atomic radii increases. Now, it increases because the principal quantum number also increases. There is a greater probability of finding electrons farther from the nucleus, and therefore, as you can imagine, the size of the atom has increased. When you move across the periodic table, when you move across the period, the size of the atomic radii actually decreases, and it decreases because the effective nuclear charge, which we just talked about, increases. And so when the effective nuclear charge increases, that causes the electrons to be drawn closer to the nucleus because they're being attracted by the larger effective nuclear charge, and so they're being brought towards the nucleus. We're now going to quickly talk about ionic radii, so the radii of ions. As you can imagine, cations, they are smaller than their parent atoms, and the reason why is because in order to create a cation, you have to lose electrons, and those lost electrons occupied outer orbitals, and therefore there are less electron-electron repulsions, and therefore the size of the atom itself, which we measure by the outermost electron, has decreased. Now, for anions, since I'm adding electrons, it's going to get bigger. It's going to be bigger than its parent atom. And the reason why is because they gain electrons, and that increases the electron-electron repulsions, which causes them to spread out even further. Now, if you notice below, I have oxygen with a 2- charge, fluorine with a -1 charge, sodium with a +1, magnesium with a 2+, and aluminum with a 3+. I want you to look at this, to pause the video and look at this, and decide what an isoelectronic series is if what I've provided you right here is an isoelectronic series. So pause the video and think about it. Look at the number of subatomic particles that each of those has and try and figure it out. An isoelectronic series is a group of ions that have the same number of electrons. So as you can notice, all of these have a total of 10 electrons. An interesting thing to do is to look at these ions and to compare their size. And if you notice, aluminum, while they all have the same number of electrons, aluminum has more protons. Therefore, aluminum is the smallest of those ions, while oxygen is the largest. The next characteristic that we're going to talk about is ionization energy. Ionization energy is the minimum energy required to remove an electron from the ground state of an atom or an ion. Now, ground state meaning it's not excited, it's in its typical energy level. The important thing for you to know, first of all, we've already talked about ionization energy when we were talking about PES. But ionization energies are positive because energy must be put into the system in order for an electron to be removed. Now, if it requires more energy, it's going to be a larger positive number, while if it has a smaller ionization energy, it's still going to be positive, but it will be much smaller of a number. So let's talk about the trends. As we go down a group, it decreases. Now, the reason why ionization energy decreases as you move down a group is because the atomic radius increases. So if the electron is farther away from the nucleus, then the attraction it has for the nucleus decreases, which means that the energy required to remove it also decreases. As you move across the periodic table, though, the ionization energy increases because the effective nuclear charge, or the attraction for that electron, and the size of the atomic radius decreases. So as the effective nuclear charge increases and the atomic radius decreases, that brings the electron closer to the nucleus with a stronger attraction for that electron. Therefore, the ionization energy is going to be larger because it's going to require even more energy to remove that electron. The interesting thing for you to know is that you can remove, obviously, more than just one electron, and therefore we call these successive ionization energies. Now, the first thing for you to know, looking at this table, is that the first ionization energy, I1, is smaller than I2, which is smaller than I3, smaller than I4 for all of these. And the reason why is after you remove the first electron, you're going to be removing an electron from a positively charged ion, which has an even greater attraction for that electron. So it's going to require more energy. Now, the interesting thing for you to look at is the sharp increase in ionization energies that this blue ladder shows. If you notice, for example, for sodium, the first ionization energy is only 496. The second ionization energy is 4,562. So why in the world does this sharp increase in ionization energies occur? And the reason why is that electrons, when they are starting to be removed from the noble gas core of electrons, it requires much more energy. So if you think about sodium, to remove that first electron, once that first electron is removed, you now have the electron configuration of neon. If you try and remove that second electron, it's going to require 4,562 kilojoules per mole of energy to remove it because it doesn't want to lose that electron. It has a perfect octet. It has the electron configuration of a noble gas. Same thing with magnesium. To remove that first electron, 700, that's fine. The second electron, 1400, that's fine. That increase occurs because magnesium has a positive charge once that first electron is removed. But go to that third electron, now magnesium doesn't have the electron configuration of neon. It doesn't want to do that, so it's going to increase the ionization energy by 7-fold. The last characteristic that I'm going to talk about in this video is electron affinity. And electron affinity is exactly as it sounds. It is the attraction of an atom for an electron. So it's the exact opposite of ionization energy. Now, the greater the attraction an atom has for an electron, the more negative the electron affinity will be. Okay? If the electron affinity is positive, that means that the electron will not be added to the atom, meaning unlike ionization energy, which requires energy, electron affinity releases energy when an electron is added to an atom. So if you have an extremely negative electron affinity, that means the atom is more stable with that added electron, and therefore it will accept the electron. If it's positive, if the electron affinity is positive, that means that atom did not want that electron, and it probably, number one, is not stable, and number two, that will not naturally occur. We always try and create trends and figure out trends in order to predict these characteristics from atomic radii to ionization energy, but if you look at this table right here, there aren't any real clear trends. There are a couple of interesting things, though, to look at, a couple of interesting patterns. The first one is group 5, which is nitrogen, phosphorus, those in green. If you look, the electron affinity for those atoms is either barely negative or, in the case of nitrogen, is positive. And so you wonder, why in the world is that the case? Well, nitrogen, if you think about the orbital diagram for nitrogen, it has 3 p orbitals, and they all are filled. If nitrogen had to add another electron, it would add one to an already occupied orbital with an opposite charge, and those 2 electrons that now occupy the same orbital, they would repel each other. And so as a result, nitrogen, in order to add an electron, it requires energy because the repulsion between the electrons prevents that addition. The other pattern to note is the trend as you move down a group. Okay? As you move down a group, what you should realize is that the electron affinity doesn't really change. While for atomic radii and for ionization energy, they did, it doesn't for electron affinity. And the reason why is that there are 2 changes that occur as you move down a group. The first one is that electrons, as you move down a group, because the atomic radius increases in size, electrons are farther from the nucleus. And so as a result, the attraction between electrons and the nucleus, that attraction decreases. But as you move down the group as well, because the electrons are farther spaced apart, the electron-electron repulsion decreases as well. And so the decrease in attraction for the nucleus and the decrease in electron-electron repulsions, those cancel each other out, and therefore there isn't one big trend down a group for electron affinity.